During the break, I rewrote the statement of this morning, so the rescaling theorem. So just to remind you what it is about. So one has a sequence of Riemannian manifold with Ricci curvature almost non-negative, and which Gromov-Hausdorff converges to the Euclidean space and of dimension strictly lower. Then the rescaling theorem states that there exists a sequence of renormalizing factor, lambda I, tending to infinity. There exists some compact metric space of fixed diameter, so we can prescribe the diameter of this compact space. And there exists a subset in the ball of radius 1 around pi, a subset of good points at which when you, so a subset of good points which are almost dense in the sense of volume in the ball of radius 1, and at which when you blow up the space, then you make emerge some fiber, K, and the important fact about this statement is that K doesn't depend on the good point you have chosen, okay? And so I started also to rewrite the tool we will need in order to prove the theorem. So there are two parts, and today I hope I will, I'm pretty sure that I will do the first part of the proof. So one of the tools is the Chigger-Colding theorem that everybody has known since last week. So which start with the same assumption. You have a sequence of Riemann manifold with almost non-negative Ricci curvature, which tend to Rk. Let's say that k is less than n, the case which we are interested in, and assume then you can find a Gromov-Hausdorff approximation of this Euclidean space by harmonic functions defined on larger and larger balls, okay, which satisfies those properties. So the functions are harmonic, the gradient of those functions are bounded, and this condition, which amounts to saying that they behave like Euclidean coordinates, okay, in Rn. Okay, right, and we had this product lemma, which looks like very much this one, but which is some kind of reciproc of this statement, which says that if you have a sequence of manifold with almost non-negative Ricci, and if there exist, so here the harmonic functions are part of the conclusion, and here you assume that there exist, so M is of dimension n, say, and assume that there exist k sequence of harmonic function of, say, a ball of larger and larger radius to Rk, so k is less than n, such that, so again, Bji are harmonic, the gradient, same assumption, the gradient are uniformly bounded, and so I forgot to say here that in here the conclusion is this kind of estimate for any r in between 1 and Ri. This is what comes from the Chigger-Colding theorem. And here in the assumption there is a slight difference, which is that you assume that this condition is satisfied for all radius. Okay, so for any, so the integral of the average on the ball of radius r at pi of hi tends to 0 for any positive r, okay? All right, so maybe, and so the game now is to use those two theorems to prove. Maybe I could. Sorry. And the thing I will start to prove today, this afternoon, is the first part of the statement, which is that there exists a good point set. I have to explain you what it is. And there exists some rescaling factor. So the good set satisfies the volume proportion property. Such that for any choice of good point, then lambda I mi pointed at any of such good points, Gromov-Hausdorff converges up to some subsequence to Rk cross k, and here the diameter of k is less than 1 over 100, say, and a priori k depends on qi, okay? So this was exactly the statement I stated this morning, and this is what we are going to prove right now, okay? Okay, so we first deal with what is this good set point, okay? So what we have is by Chigger-Kolding we have a set of harmonic function, okay, k harmonic function with good properties, okay, and in particular, we know that the average of the function hi on all balls of radius r tends to 0, okay. So let's write some precise way. So let's choose some sequence tending to 0, and let's assume that this quantity is of order epsilon I to the 4. It doesn't matter. You can always choose such a normalization. But this is true for R between 1 and Ri. Okay? And we want to, of course, we want to use the second statement, the product lemma. Okay? And then we need to check. So we want to use the product lemma. And then we need to check that such an assumption still holds for any radius. Okay? So we have to pass from this set of radius to any radius. So we need to check that this integral tends to 0, maybe not everywhere. So at some tends to 0 on a subset of good points, which I will describe now. Okay, and for all R positive. Okay. So first of all, so the set of good points. I am looking at this set inside the ball of radius 1 in Mi, okay? And I want to so the set of good points will be points at which this property holds. And there is one thing which is completely trivial, which is that if R is already large, then this condition is trivial because it comes from the earlier one. So if R was greater than 1, then of course, for any Qi in the ball, so here I have not to choose special points for any point in the unit ball around P1, then if I compute the average on the ball of radius Q1 of Hi, then certainly it will be less than the average on the ball of radius, let's say, R plus 1 around P1. And here I have made some mistakes, which is a ratio of the two volumes. And we get a constant, a term, which is volume of B R plus 1 Pi divided by volume of BR Pi. And this term, since R is larger than 1, it is bounded above by Bishop-Gromov inequality. Okay? So this term is bounded above. This term is bounded above by some constant, which depends on the dimension and on R, and which is exactly the ratio of the two volumes in the space of constant curvature equal to the lower bound on the curvature. Okay. So there is a constant here, and which is uniformly bounded if R is bounded away from 0. Okay. And then this term tends to 0. Okay. Just by this assumption here. Okay. It's of order epsilon I to the 4. Nothing to say. Of course, the case which I am interested in is the case where R is in between 0 and 1. Okay? And here I have just to do some standard trick of measure theory, which is the following. So I have to recall you some definition. So if you have a map, a function, a positive, a non-negative function defined on some Riemannian manifold, you define the maximal function of RD Littlewood as, maybe you probably know that, but I just recall the definition. So you fix some positive number, and so you define max rho of f of x. So it's a new function on M, and this function is the sup of all among all radius which are smaller than rho of the average of f on the ball of radius r, centered at x. Okay. So this is the maximal function of RD Littlewood. And the fact which we will use about this maximal function is that for any rho, let's say in 0, 4, bounded rho, say, if f is in L1, so if f is integrable over M, then the set of points where the maximal function is larger than C. So this function could be infinite at some point. Okay, but if f is L1, then you can control, in some sense, the regularity of this maximal function. And you have the following estimate. So the volume of the set where the maximal function is large is controlled by the L1 norm of f. Okay? up to this factor. So this fact is completely you can find it on any textbook on integral and integration, and it remains true on manifold with lower bound on Ricci curvature, because the argument in Euclidean space relies on the doubling property of the volume in the Euclidean space. And on spaces with Ricci curvature bounded below, you have the doubling property. And then you have this same proof proves this fact. Okay, so so now what you have to do is completely obvious. So you apply this to, so you consider, so you apply this fact to f equal hi restricted to b1 of pi, and and you get that the volume of the set of points where the maximal function, say at radius 2, for example, it's not important, where this maximal function is larger than epsilon I to the square, that's why I took epsilon I to the 4, is less than some universal constant divided by epsilon E to the square times the integral of hi over the ball centered at pi of radius 1. Okay? And then if I take this, the volume of the set of those points where inside the ball of radius 1, okay, it's still true. And if I look at the proportion of volume of this set, then you get this with an average here, and this is of order epsilon I to the 4, and then this is less than, this tends to 0, okay? So what we have done so far, we have found, so what this allows to say is that if I consider the subset of points of B1, which is complementary of this one, you get the subset we are looking for. So let's define now G1 of Pi to be the set of points such that the maximal function 2 of hi is less than epsilon I, and we know that the volume of G1 Pi divided by the volume of B1 is larger than 1 minus c of n epsilon I to the square, so it has a good proportion property. And we also know that for any good point, for any point in this subset, then the maximal function of hi at q is less than epsilon e to the I to the square, and which implies that for any r less than 2, okay, the average of hi tends to 0, okay? Is less than epsilon I to the square. Is it clear? It's something completely straightforward, okay? So I have just used the maximal function, the property of the maximal function of Hardy-Littlewood to say that this set has a good property with respect to the measure, and by definition of this set, we have this property. Okay. Okay. So it was just, I mean, it is just something which allows to pass from a defined scale here coming from the, so in the Chigger-Kolding theorem, you have some property which is defined on a certain scale, r larger than 1, and you want to push this property at all smaller scale, and this is what this RD Littlewood function does for you. Okay? Is it all right? Okay, so maybe I, if there is no question. Okay. All right. So now one has to choose lambda I tending to plus infinity. Okay. So I have not. Okay. So at the moment I have just defined some subset where one has some property. So I have not started to prove anything actually. Okay. So what we want, I recall you that what we want is to choose some renormalizing factor such that for any good point, one has this property, right? With diameter of k of given order, okay? And so far we have this, and we want to apply the product lemma, okay? So this property tells you that, so what we have done so far is that for any q in B1 in the set of good points, then one has the right assumption, right? Okay. Then then we want to apply product lemma, and the remark, and so the remark is the following. So, all right. So, okay, sorry. So I have to find the right scale here, and so for each, so by the product lemma, okay. So far I have this, and I have to make some remark. Sorry. The remark is the following. So take any rescaling factor. So at the moment I don't know which one is a good one, but take any rescaling factor, and I claim that the condition of the product lemma still holds for this renormalized manifold. So if I consider the dilated mi according to this choice here at a good point, my claim is that if I look at the function lambda I bji, so what I'm saying is the following. So at any good point and for any rescaling factor, then the rescaled harmonic function I have, okay, satisfied the property of the product lemma. Okay, so this is the remark. So for any rescaling factor, this set of functions satisfies the assumption of the product lemma. So this is just, I mean, you could say, why is it so? It's just because the function hi is a scale invariant if you multiply everything by lambda I. So the reason is that if you look at bji and you look at the gradient of this function, so the condition on this function I have to check is a condition about the gradient and also about the Hessian. And the condition is the following. So if I look at the gradient with respect to lambda I mi of this function, then it is just the gradient for mi of bji divided by lambda I. Okay, so that's the term which I evaluate, which is hi, the sum of all scalar product of this function. So let's say, so now I compute with respect to this metric and for this function. And the claim is that if I compute those scalar products, then this is equal to so here you have 1 over lambda I to the square because of this formula, and here you look at the scalar product with respect to lambda I mi, and so you have a lambda I to the square which appears, so it's scale invariant, okay? So it's sorry. Okay, so that the conclusion of this discussion, and the same for the Hessian, and the conclusion of this discussion is that for any rescaling factor, if you look at this rescaled function, then they satisfy the assumption of the product lemma, and then a subsequence of this rescaling thing converge to arca some a product. So the conclusion of the product lemma is that lambda I mi qi, so for any lambda I at the moment, and any qi in the set of good points, then this converges, a subsequence of this converges to rk cross y. Okay, so at the moment I have not, I don't even know if y is compact. Okay, so what I say is that for any rescaling factor, I can apply I can say that a subsequent converge to rk, same k, cross some metric space. Okay. So now I come up with choosing the right lambda I. Okay. So is it okay so far? So I have done almost nothing up to now. I have just said that for any rescaling factor and any good points, I can apply the product lemma and I have this conclusion. Okay. Okay. No questions? So now, in order to define the right rescaling factor, I consider a good point. And I look at what I see at around this good point. Okay, so what I know, of course, what I know is that mi before rescaling, what I know is that this looks like rk. This looks like rk, right? Before rescaling, it is the assumption. So mi pi converge to rk, and so for any other point nearby, you have the same limit, okay? So this is before rescaling, okay? So what you see is the following picture, some kind of rk. What you see some box. So if I look at the ball of radius 1 around qi, I see some kind of box, which is not really a box, but let's say of size 1 here, and of 8, the distortion of the Gromov-Hausdorff approximation, which tends to 0, okay? So some kind of distortion here. Okay? And, and I define rho of Qi to be the right factor, the correct radius, such that if I look at the ball centered at Qi of radius this thing here, I will see a box of reasonable size, meaning a box of basis of length rho of Qi and of 8, let's say, rho of Qi divided by 100. Okay? So I claim that there exists some scale around Qi such that I see that. Okay? I see so that the ball of radius 1 around Qi in Mi looks like a kind of box with this dimension. So the definition is completely obvious. So I define rho of Qi to be the maximum of rho in the interval 0, 1, such that the distortion, of the function. So I recall you that the harmonic function defined Gromov-Hausdorff approximation restricted to the ball of radius rho around Qi is exactly rho divided by 100. Okay. So there certainly exists some kind of some rho of Qi which has this property. Okay, and note that this number, this radius, has to tend to 0. So my claim is that it's impossible that for a fixed rho far away from 0, the distortion of Bi on this ball is equal to rho divided by 100, a fixed number, because we know that Bi are Gromov-Hausdorff approximation, and then on all fixed ball, the distortion tends to 0. Okay? So there is certainly a sequence of radius which tends to 0, and such that Mi Qi looks like a reasonable ball of size rho of Qi and rho of Qi divided by 100. Okay, and then what comes out from this is that if I renormalize by this factor, then the whole thing Gromov-Hausdorff converge up to some subsequence to Rk cross k with diameter of k equal 1 over 100. Okay? Because I have just, the distortion is rho of Qi. Okay? So if I multiply by rho of Qi, the distortion at the limit will be exactly 1 over 100. Okay? I say something completely basic here. Okay? Okay, but now, and then in order to prove what I said before, I have just to consider lambda I. So what is the right factor, the right renormalizing factor? It will be the maximum of such rho of Qi. So if you choose now lambda I equal the sup over all the good points of rho of Qi, and what we have done is and conclude that for any Qi now in a set of good points, then this sequence converges to Rk cross k, where the diameter of k is less than 1 over 100, of course. And if I take, so because here I take any sequence, okay, so since I have taken, oh yeah. So it's 1 over, so I have, Okay, sorry. Yeah, right. So I define rho I to be the sup, and lambda I is 1 over rho I. Yeah, sure. Thank you. Yeah. Okay. Of course. And then I get this, and certainly there exists. So this is for any sequences, and certainly there exists a particular sequence of good points, such that you converge to Rk cross k. So here a priori the k depends on the sequence I have chosen. Okay. Here the k depends on Qi. Okay. And there exists certainly a particular sequence of Qi where you achieve the maximum, such that the limit raise the factor k, which has diameter 1 over 100. Okay. So here we are. What we have done so far is that we can choose a set of good points, and we can choose a rescaling factor such that when I blow up the space at any of these good points, then I come up with a product where k depends on the sequence. Okay, and the diameter is not larger than 1 over 100. And for some sequence, I can get one fiber which has diameter 1 over 100. Okay? I'm sorry, it's a bit technical, but it's not very complicated. So maybe I shouldn't erase. Oh, yeah, maybe. So in order to complete the proof of this first step, I would like to explain you how to prove this product lemma, which is the key tool in this in what I have done here. Just to relax. I hope so. Maybe where is the product lemma? Did I erase it? Yes, I erased it, yeah. Okay, never mind. Okay, so let me just explain the sketch of the proof of the product lemma. So we have a sequence of manifold and a sequence of function, right? Harmonic function with good properties. With three properties. Harmonic, uniformly bounded gradient, and this bound on HI. For any ball centered at some for any ball of positive radius, okay? For any ball. Okay, then the idea is the following. So right, and the conclusion is that what we want to prove is that mi Pi converge to Rk cross maybe something. Okay? So one has this family of harmonic function, and we want to show that the sequence subconverge to some. So we know that by Gromov precompactness theorem that some subsequence converges, and we know that if there is a line at the limit, it splits, but we don't know that at the limit in the limit. So we know that a priori what we know is that, so this is what we want, and a priori what we know is that it converges to some space X. Okay? And we know by the almost splitting theorem that if there is a line here, then it splits. Okay? So let me just explain you the proof of that when k equal 1 to simplify. Okay? The same for all k. And so, so we know that, and by the almost splitting theorem, it suffices to prove that X contains a line. Okay? And the way we are going to do it is the following. So we okay, so what do we have? We have a sequence of mi and a sequence of functions. So I have just one function because k is equal to 1. So I write it bi, this function. And this sequence of harmonic function has bounded gradient. And so from some Ascoli principle, so I know that this converges to some metric space, X P infinity. And then by some Ascoli principle, then this function will certainly converge to some function here. Okay? And the way we are going to prove that there is a line here is to prove that this function here is a submetry. So the submetry is some notion which is a generalization or a natural generalization of the Riemannian summation to metric spaces. So let me just define what a submetry is. So take any function f between two complete length metric spaces. And we say that f is a submetry if for any x in X, any radius, the image of the ball of radius r, centered at X, is exactly the ball of radius r centered at f of x. Okay? And a good thing about, so for those who knows, you know that when you have a Riemannian summation, you can lift horizontally geodesics. And here, the fact which I may let you as an exercise is that is that if F is a symmetry, then any geodesic in Y lift horizontally in X. So let me just give you the hint to do the exercise. So you take a geodesic downstairs on Y between 2 points, let's say Y and Y prime, and you want to find a geodesic here which projects down to the geodesic downstairs. And then what you do is to first you choose any lift above Y, and you subdivide the geodesic here in many small intervals. Okay, and because of this property here, you certainly can find. So let's call this point X and this subdivision Y1, etc., 1J. And then you can certainly find point here above those points, okay, such that the distance here is the same. I mean, such that this point is in the ball of radius r. And then you come up with a sequence of curves upstairs, which has the same length as downstairs, and when you refine the subdivision, then you converge to a geodesic. So I let you finish the exercise, okay? But it's so refine the subdivision and get the lifted geodesic. Okay, so then here, if I can show that B infinity is a submetry, then I can leave this geodesic here, and so I will get a line here, and then I apply almost splitting, and I have what I want. Okay. So let's prove that B infinity is a submetry. Any question? Okay, so many. So we prove that B infinite is a submetry. And in order to do that, I will need some statements that you have probably seen last week, which is the segment inequality of Chigger and Kolding. So let me just restate it. So the idea is very simple. In fact, the idea is that one knows that the gradient of the harmonic function are behave like a gradient of coordinate function in Rn, and therefore their integral flow line should be geodesic. This is the idea, okay? And so the segment inequality is typically the thing which allows to formalize this. And what it does say, so you take any manifold with Ricci curvature bounded below, and take any two points somewhere, x and y, and take, so P's, so X and Y are points in M, and choose some positive number delta, and look at the ball, the two balls of radius delta around X and Y, okay, and consider the integral of, and first of all, you need some function, sorry. So G is a non-negative function, a continuous function on M. And then you are going to consider the integral over all. So you are going to choose a point here and a point here. So let me just, okay, so x1 and x2, okay? So those 2 points are x1 and x2. And pick up any point x in the first ball, any point y in the second ball, and choose for any such choice a geodesic, a minimizing geodesic, which I call gamma xy, okay? And look at all possible choices, okay? So for any pairs of points in B, the ball around x1 and x2, you choose minimizing geodesic, and you look at the integral over each choices of pair of points of the integral over the geodesic of the function g. And it's controlled by the integral of g on the larger ball. Okay, this is what the segment inequality says. So let me just write it down. So it says that the integral over the ball b delta x1 cross b delta x2 of the integral over b. So I choose 2 points, x and y, and I look at the integral along the geodesic between x and y of g. And the claim is that this is controlled by some constant depending on okay, so I forgot to say something. So there is a point P here, which is here. And let's say that the whole thing here is contained in the ball of radius 4r, okay? There is some constant radius here, r, which contain these balls and all the geodesic joining any pair of points here. And the claim is that this is controlled by a constant depending on the dimension and the size of of this ball I have just chosen, time the volume of the ball, the sum of the volume of the ball, centered at x1 and x2 of radius delta, times the integral over this larger ball which contains everything, b4r around p of g. Okay? And so it allows to say that if a function is small, in average, then is small, the integral of function is small, then you will be able to find a lot of segments on which the integral of g is small. This is the idea. So you probably have seen this kind of statement last week. It is useful in the proof of the almost splitting theorem, or it may be useful. Or maybe you have seen another version. There are several versions. Have you seen this? Okay, yeah, you have seen this. Okay. So this is the tool. So now I want to use this to prove that B infinity is a symmetry, and I start showing that B infinity is one Lipschitz first. Okay? So I recall you that B infinity is the limit one has this sequence of functions between Mi and function on Mi, which converges to B infinity on the limit space. Okay, and I want to show that B infinity is one Lipschitz, and it's almost obvious what one has to do. And let's do it. Okay, so I want to show that. So I take 2 points here, x and y. In y, okay, and I want to show that B infinite of x minus B infinite of y is smaller than the distance between x and y. Okay, and so I can approximate x by some sequence of points, x in Mi, xi and yi, okay, so which converge to x and which convert to y. Okay, and of course this difference I want to estimate is the limit of the bi of xy minus bi of yi. Okay, and what I will deduce the one Lipschitzianity of this function from the fact that this is less than d of xi yi plus delta for any delta. Okay, it's exactly what we want to show. And to do that, I look at okay, so I look at so I apply the segment inequality to the function g equal to the gradient of bi to the minus 1, okay? Which is, okay, so we know, what we know about this function is that we know that for any r, the average on any ball of radius r around pi of this function, so let's call this function hi, so it's not the complete hi. I've just forgotten the Hessian term, but I don't need it in this part of the argument, okay? So I denote hi this function, and what we know is that this tends to 0, right? For any r, okay? And so I apply segment inequality to this function, okay? And what I get is that the integral over the two balls, the product of the ball, around xi and yi, of the integral between 0 and the distance between x and y of, let's say, g gamma xy of t dx dy, okay, is smaller than some constant, time 1 divided by the, the volume, the sum of the volume of the ball, times the integral over a larger ball around pi of g. Okay? So g is hi. Okay, so now if I if I consider the average of this integral here, so I divide by the product of the volume of these two balls, okay? I come up with this divided by the volume of B delta. So I divide this term by the product of the volume here, and so I transform this sum by the sum of the inverse, Okay, so I get 1 over the volume of B delta of xi plus 1 divided by the volume of B delta of yi times this, okay? And now I claim that this is not far from being the average of hi on this ball, again by Bishop-Gromov inequality. And say I claim that it is less than C of nr times another constant depending on r and delta, okay, time the average of hi over the over the ball of radius 4r. And this new constant here, it is just the ratio between the volume of this ball. So let me just write down what is this constant here. But I think you have understood what I'm doing here. So here's the new constant. C of n r delta is just the ratio between the volume of the ball centered at 4r, centered at pi, and divided by the volume of B delta, let's say xi, 1 or 2, and this is bounded, right, by some constant. This is bounded by some constant, okay, by Bishop-Gromov. All right, so what do we have here? So this term now tends to 0, and then we have that on average, all these functions are small, which means that for a large proportion of points in the product of ball, the integral along the geodesic is small, okay? We have a function here, whose average on some subset tends to 0, and so I mean that I want to conclude that for most of a pair of points uv in those balls, then the integral between 0 and d of uv of g, so which is a gradient of vi minus 1 along this geodesic uvt is small. Okay? Do you believe me? It's just a usual trick, okay? And then it means that if I consider so I am in this ball here, the huge ball, and I have those 2 points xi and yi, which converge to x infinity to x and y. In the limit space, and what I say is that for most of this of pair of points here, then you have that along the geodesic joining u and v, this function has small integral, okay, and this is enough to show that the distance between xi and yi it's enough to show that Sorry, I'm lost. But, right, so. Okay, so it's okay, so. Okay, so it's almost finished because we have that. So we want to estimate this difference here, which is a limit of bi xi minus bi yi. And of course, this difference here is not far. So it's up to. So we know that the function bi are Lipschitz, okay, are L Lipschitz, uniformly Lipschitz, in such a way that this difference can be up to 2L delta, estimated by the limit of bi of ui minus bi of vi, where ui and vi are points that I have chosen here, okay. And of course this is almost okay. So this is okay. So since the function is of gradient of integral close to 1, then this is less than 2L delta plus the distance between ui and vi, maybe up to some factor, okay? Okay, we have a function whose gradient is 1 in integral, and then the difference between the extreme value are less than the distance, okay? Just by standard thing. And then passing to the limit, we get that it is less than distance between x and y, because the distance between ui and vi is converging to the distance is converging to the distance between x and y, okay? Because these 2 points, and xy and yi, converge to x and y, and so does ui and vi. And so what we have done is that we have shown that this is less than this plus maybe 2L delta. And delta was arbitrary, and so we get the Lipschitzianity of the function, okay? So I probably messed up this a little bit, but it's very simple, okay? So far we have just shown that B infinity is 1 Lipschitz, okay? And we are looking, and we want to prove that B infinity is a submetry, okay? So we have done half of the job. And let me just finish. Is there any question here? No? Okay, so we want to prove that B infinity is a submetry. And we have proved that, the image by B infinity, we have proved that B infinity is 1 Lipschitz. And so we have proved that the image of a ball of radius r centered at any point y is contained in the ball of radius r centered at B infinity of y. Okay? And so we need the reverse inclusion. Okay, so let's draw a picture. So one has y here, and this limiting function. So let me just write it to the side. So I have y here, and this limiting function on R. And I take some point y here. Okay, and so B infinite of y is here somewhere. Okay, and I want to prove that any ball, so any interval any interval of radius r around b infinity of y is is achieved by a point in the ball centered at y. Okay, and the way we are going to do it is to prove that we can find a geodesic through y which project down to this geodesic, and a geodesic of arbitrary length. Okay? So if we can do that, if we can prove that through y there exists a geodesic segment of size, of any size, which project down here, then we will have shown what we want. Okay? And so far we have not used yet the fact that the function bi are harmonic, and we are going to do it right now. So it's the same kind of argument as before, and let me just do it now. Okay, so I look on this side of the picture. So here it's the side of y. Here one has mi, which converge to y. And so there is the base point here. And our point y is a limit of some sequence of points yi here. Okay? And I look at a huge ball around pi, which contains all those points. Okay? And I look at all the integral lines of the... So I look at this vector field on mi. And let me just call phi t the flow of this vector field. And so one has a lot of flow lines here. Okay. And I will, so the idea is to show that close to y, so the idea is so what I want to do is to find a geodesic here, okay? And the geodesic here, C infinity of t, through y, which project down to this geodesic here, to R. And this geodesic will be an image, the limit of a sequence of integral curves of this flow. Okay? This is so the idea I mentioned earlier is that the integral line of this, the flow of this vector field should have integral lines which would looks like geodesic, and it's exactly what we are going to prove. And how does it work? So you start by computing the average. So let's still consider this function. So this function, which is just the hi, which we know being small on average on large balls, and then I take some parameter, let's say t0, and I compute the integral. So I take a point on this large ball, any point on this large ball, and I compute the integral. Maybe we will switch the order. So I will compute the average on this large ball around pi here. Okay, so I look at all points on this ball, and for each point I look at the integral curve and at the integral along the integral curve of this function. So I compute this. Okay, so I took a point here and I have average, and I compute the integral of the function hi on this geodesic here. So here I compute this, and so this, and I take the mean value of this, and of course, this can be written down as can switch the integral terms, and I switch the integral terms, and I can just do a change of variables, and recall that phi t is a flow of a vector field, which is a gradient of an harmonic function, and then this flow preserves the volume. And then by usual change of variable formula, you get that this is exactly the integral over between minus t0 and t0 of the average on phi I t of the ball of radius r around pi of the function hi of phi of z dz. Okay, and then dt. You follow me? And then so here I have used the fact that phi ti is preserving volumes, and of course this ball here, since the gradient of the harmonic function here are uniformly bounded, then we know that we don't go too far away, and this set is contained in a ball of radius, say r plus 2l t0 around pi, just because L is a bound on the gradient of the function. So I don't go too far. And then this integral is certainly less than some constant, depending on n and r and L and t0 of the integral of hi over this larger ball, okay? And then it tends to 0, and again, you come up with the fact that on a great proportion of points z, then this function tends to 0, okay? Same argument as before, and maybe I will let you finish the exercise, or so what we get is for a large proportion of points z in B pi of r, then we have that the integral between between minus t0 and t0 of hi of phi I t of z dt tends to 0, okay? And from there it's not difficult, it's the same argument as before. So maybe I let it for you. Or maybe I do it, maybe. It's not exactly the same argument. Okay, so so from this I can certainly find a sequence of points zi arbitrarily close to yi, okay? And so I will call this such that the integral is so choose, okay, so we have this, and then we can choose zi such that the distance between zi and yi tends to 0, and such that the integral here of hi on these curves tends to 0, okay? Because it's true for almost all points. So here I have a point which is nearby y, and the integral line. So let's call Ci of t the integral line of this through this point Zi. Okay, and the claim is that first Ci of t converges to some curve C infinity of t through y, okay, just by construction, okay. And if okay, so maybe I should have mentioned something here. So hi is just this function here, okay? Is the norm of the gradient of Bi minus 1 in absolute value, okay? So what we know is that this tends to 0, okay? But what we know also is that the same thing works exactly the same with a factor 2 here, just because this number is smaller. When I add a factor power 2 here, this is less than. Okay, so I have explained you why this tends to 0 without the power 2, and I just say now that it is also true with the power 2, just because pointwisely this function is less than this one. Okay.
What was this function CIT?
CIT is the limit. So CIT is not a function. I have called the integral curve through Zi Ci of t. It's a path. Okay. And my claim is that the first claim is that this sequence of paths do converge to some path through y. Okay. Again, because the speed of these curves are controlled by the gradient of Bi, which is uniformly bounded, so it converges. Okay.
Did you use
Yep.
this argument that this function B is harmonic?
Yes, I have used. Okay, right. I have used it here. So when I have done this computation here, so when I say that this integral here is this integral here is equal to this thing, okay, and here I have done the change of variables, okay. I have put this as a variable, okay, and I have used the fact that the flow of a harmonic, the gradient of a harmonic function preserve volume. Okay, so that's where I have used this, and that's why these two terms coincide. Okay. Okay. So this curve converges to this one, and I claim that the length of Ci converge to. So Ci is just a curve parameterized between minus t0 and t0, and the length is just converging to 2 t0. Okay, just because we have just because this integral here is small. Okay, and also we have that Bi of Ci of minus t0 minus Bi of Ci of minus t0 also do converge to 2 t0 because of the second estimate with the power 2 here. Okay, and just because this difference is comparable to the integral between minus t0 is equal to the integral between minus t0 and t0 of the gradient of Bi to the square along the geodesic, okay, along Ci of t, along the curve. It's not a geodesic. Okay, and so I have these two properties here, and since this converges to B infinite of C infinite of t of t0 minus B infinite of C infinite of minus t0, okay, which is less than the distance between those 2 points, because B infinity is 1 Lipschitz, and which is 2 t0 because it converges to 2 t0. And this means that this means that this curve C infinity is a geodesic. Okay? So it's a geodesic through Y, okay? So it certainly covers this ball of radius, of any radius. T0 is arbitrary, so it covers this any segment around B infinity of Y, and then the B infinity is a submetry. And then we can lift geodesic and apply almost splitting and blah blah. Okay, so this finished the proof. In principle, it finished the proof of the product lemma. I hope it was not too technical. And maybe it's the right time to stop. And so tomorrow, so far I have completely showed the easy part of the rescaling theorem, and I have absolutely not talked about the more complicated part. And maybe so tomorrow maybe I will say just a few words, maybe 5 minutes, how we do this. It's very technical, and maybe it's impossible to tell in reasonable time. And I will start with the other important theorem of the paper of Kapovitch Wilking, which is a short basis theorem, and which is very nice thing, and which relies on the kind of arguments they use all along the paper. So contradiction argument with induction of the dimension. So that's for tomorrow. Thank you.